Yeah, so as Harry already mentioned, we were very fortunate to be able to hire Jonas Helsen very recently, paid by this Quantum Software Consortium Gravitation Grant. And Jonas is going to tell us about his research, which interfaces a little bit closer with the actual construction of quantum computers than what most of us do in QSoft. And at the same time, this is also an opportunity for Jonas to kind of introduce himself to the Institute. So Jonas, please go ahead.
Right. Okay. So hello, everyone. So as said, my name is Jonas, and starting in September, I'll be a tenure track researcher at CWI in this quantum software grant, and also so at QSoft. And the things that I am really interested in are sort of, as Ronald said, sort of the interface, basically where the rubber hits the road. So I'm interested in running things on actual quantum computers, not as they exist in some hypothetical form in the future, but as they exist right now, which means I am interested in quantum computers that don't really work. In particular, they're sort of affected by noise and they have errors whenever you try to do computations. And one of the two sort of things that I'm going to talk about now is in particular how to characterize this noise and this error and how to mitigate it. Where by characterization, I mean, can we sort of classify what type of error it is and how bad it is? And mitigation is, what can we do with it? And I'll be a little bit more precise about what I mean by that word, because it has a certain technical meaning. But let's give a little bit of an overview. So what do I mean when I say noise? Well, we had Harry set this up quite nicely for me. There is this notion of an ideal quantum computation where you, if you want to run some quantum algorithm, you set up a few qubits, maybe you set them all in the 0 state, and then you apply these quantum gates to them. And in this example, it doesn't really particularly matter what gates they are. And in the end, you measure and you get some classical information out, and maybe that classical information encodes the solution to some problem you have. But of course, if you try to do this on a real physical device, maybe these are electrons or an ion trapped in a magnetic field, they're going to be influenced by all kinds of external factors that you can control, and also maybe the things that you can control you're not controlling entirely perfectly. So in practice, maybe your state preparation goes wrong, or some of the gates you do, some errors creep in, or maybe they just fail entirely. Like a toy model that you can always keep in your head is that with a very small but non-negligible probability, one of these gates just fails and produces random output. So instead of some nice qubit state, you just get some random state back, which is not really what happens, but that's a good toy model to keep in your head. And so the goal is, for us, is to deal with this reality. And I'm going to go a little bit deeper into that, basically. So there is this noise, and the question is now, what can we do with it? Because this is a fact of nature, and there is not really, at least in the short run, say the next 50 years or so, there's not really anything we can do about it. Of course, classical computers are also noisy, but they're much less noisy. So there, a little bit of error correction goes a long way. And, quite often you can pretend that a classical computer as it exists in the physical world is just, it's an almost perfect realization of an abstract Turing machine. For quantum computers, this is very, very far away from reality. We really have to take this noise into account explicitly. And when I say taking into account, in my research, I particularly mean two things. The one thing I really care about is learning things about this noise, which is what I call characterization. And when I say learning, I don't really mean this at the sort of physics level. So I don't mean what are the materials that my device are made of and are there any device imperfections. I mean this more at the level of the sort of computation itself. Like, what is the effect of underlying noise at the level of a gate? Gives it maybe some probability of failure, or maybe it does something slightly different. And what does it do at the level of an algorithm? If I try to run a quantum algorithm on a noisy computer, how does this noise, which I may not care about the detailed physical form exactly, how does this noise affect the outcome of my algorithm? And then once we know these two things, you can ask the obvious question is, can we somehow correct through error correction or mitigate by doing some clever post-processing this noise, and in particular, the effects of this noise on the outcomes of this algorithm? And we really want to think about these things in a sort of device agnostic way. So the goal is to get abstract procedures that allow you to characterize your noise, to learn something that work on any type of quantum computer. And the other goal is to give these sort of mitigation techniques, things that you can sort of plug onto your ideal algorithms to make them a little bit more noise robust, really at the software level. And I want to sort of put this a little bit more into the tool chain of quantum computing, maybe, because when I say characterization in particular, but also mitigation, these things show up at different levels in the sort of quantum computing stack or the quantum computing process flow, and they are useful to different people at different times. So maybe really below at the physics level, the people that use characterization tools are the experimentalists themselves. They're the people that are trying to make better qubits, better quantum logic gates, and they have their own little feedback loop with characterization tools. And I'm going to talk about characterization tools. I'm going to give specific examples later, but for now, keep this sort of abstract idea in your head. And they have this little feedback loop where they build some quantum logic gates, they specify them in some way, and then they implement them, and they use this characterization tool to test whether or not they work. And then given that information, they feed back to these quantum logic gates and make them a little bit better. And this is sort of a loop that is happening very close to the hardware level. And then maybe once your logic gates, your individual logic gates are good enough, you say, aha, maybe now I want to try and build up some actual quantum algorithms. And this puts you at a little bit of a higher level. Now you're not really caring about the individual physics anymore. You're really caring about a quantum algorithm that gives you the solution to a certain problem. Of course, as I said before, these quantum logic gates are never perfect, no matter how hard you try. So the direct route here is not going to work. There will be noise, and this noise is going to basically ruin the computation. So it might give you, with some probability, a completely random answer, or maybe it'll always give you a slightly wrong answer. There's many ways in which this can go wrong. So taking this direct route, just naively implementing your algorithm, isn't going to work. And then in order to deal with this sort of blocked path, there's basically two things that people have come up with over the last 2 decades or so, which are sort of side routes, and they are quantum error correction and error mitigation. And I want to really emphasize that these are two different things. Quantum error correction is really saying, okay, I am going to, like classical error correction, encode my qubits and my gates in a redundant fashion in a way such that I can, as long as my noise levels are low enough, I can emulate a smaller but perfect quantum computer. And this sort of works independently of any noise model, as long as the noise is small enough. The problem is that this is very expensive, and we can't really do it with current quantum computers, but this is sort of the end goal. But in the meantime, we want to use the quantum computers that we have. So we're going to go for something asymptotically less optimal, but maybe more useful in practice. And this is error mitigation. And this is sort of a change of strategy. It's saying, okay, I'm going to run a quantum algorithm, maybe in a slightly adapted form, and I'm going to characterize my noise in some way, and then use what I know about this noise to maybe correct at the end of the calculation some errors in my outcome. So maybe I know, oh, the first bit is always flipped. Then if I learn that, I can just always fix the first bit whenever I make a measurement, and I get the correct solution again. And here there is a second feedback loop with characterization tools, where you really have sort of at a circuit level, your characterization systems being used to test a whole quantum algorithm, and then sort of feeding back up this classical information to sort of correct for any noise. And of course, this is a limited process, but it works reasonably well in practice. So these are sort of the two areas where abstract methods of extracting information about noise in physical quantum computers are useful. And I mean, I've told you now where they are. I've told you where to find them, but I haven't really told you what they are and, you know, how to use them. And I want to illustrate what a quantum characterization tool looks like by using a particularly popular example. And it's going to look a little bit abstract, but at the end, hopefully you'll see at least why I'm interested in these things. And it's going to look a lot, this characterization tool that I'm going to talk about is called randomized benchmarking. And it looks a lot like the supremacy task that Harry talked about before. So basically, the idea is that we're going to run little random computations of increasing length. So there is a length m. I'm going to run a little random computation, but I'm going to do it in a very special way. Namely, I'm going to run a random computation, and then I'm going to create sort of the inverse of that computation, so that ideally, what I've done in the sort of an abstract perfect quantum computer, I would have done nothing. So I sort of know what's going to come out in the end. And I'm going to do this for varying lengths, and I'm going to do this for very many random computations. And if you do this correctly, and it turns out that this works reasonably well, if you pick the correct set of random circuits and you compile them in the correct way and you make some assumptions on your underlying noise, it turns out that this probability of seeing the identity again, so this fails with a certain probability that depends on m, is going to be almost exactly an exponential decay, which when you think about it, makes sense, right? You sort of, if every operation here is a fixed probability of failure, then the total probability of failure is going to be that fixed probability to the power m. But of course, most quantum computations have noise models that are much more sophisticated than that. So arguing that in general, this thing is an exponential is reasonably non-trivial. And it turns out that then the decay of this exponential gives you some estimate of how well your quantum circuit, your quantum algorithm block works on average. And, you know, maybe that's not very useful information, but it's a little bit useful. It's sort of a first order approximation to how much your particular circuit fails. And now, you know, I've given you some specification of an abstract procedure, and people actually do this in the lab. But of course, just giving you this procedure doesn't mean that this thing actually works as advertised. And I've sort of left a lot of things unfilled in. For instance, I haven't told you what the set of circuits is that you're going to be sampling from. Like, what types of random circuits are you picking? Also, if I want to see this exponential and I want to have this decay rate mean something, this is not necessarily informed by the specification of the protocol itself. It needs to be made reasonable by making some assumptions on the actual device physics. Because, for instance, I could have a quantum computer that works perfectly on all days except for Tuesday. And in that case, this experiment is going to work really well on all days except for Tuesday, but it's not going to be giving you a good characterization of the behavior of the device overall, because it fails on Tuesdays. So you need to make certain types of mathematical assumptions on the underlying physics. And the goal is to do this to get as much bang for your buck by making as abstract an assumption as possible. So you could say, like, oh, I want my noise to be time independent. This is saying almost nothing about the underlying device physics, but it gains you a lot in terms of the predictability of these types of protocols. And then, of course, it's not clear that the thing that I've said actually works in practice, because I'm telling you, oh, sample these random sequences. But of course, there's sort of exponentially many of these in M. Like if you sample a sequence of length M and you have some sets to sample from, you can't possibly enumerate them all because you'd be busy forever. So there's non-trivial questions about the sample complexity of things like this. And these are really the questions that I care about. And I care about them for mathematical reasons, but also because experimentalists really care about this. Because they need to know how many samples they're actually going to take whenever they're going to do these protocols, and they need to know what kind of circuits they can test using these protocols and what kind of circuits they can't. And I'm going to focus now a little bit on this last question and give you sort of a taste of the mathematics that goes into this. By just very short, this is going to be a slightly more mathsy slide. So if you're not interested in actual math, you can zone out for a little bit now. So I'm going to talk a little bit about this statistics question. Like, okay, given that we have this randomized benchmarking procedure, and maybe we've specified a correct set of circuits, maybe we've done the correct assumptions on our device. Now, how many random circuits do we actually need in order to actually guarantee that we have a good estimate along every moment of this decay? And it turns out that this is a quite non-trivial question. So one of the useful things that you can do is try to estimate just the variance of this thing as you sample random sequences. And you can do this under suitable assumptions on your noise model in quite some generality. And if you assume that your circuits secretly form some group, so they're closed under computation, that gives you a lot of mathematical grip on this problem because it's a set of unitaries. So your mind should go to unitary representations of groups fairly quickly. And it turns out that calculating this variance is essentially a representation theoretic problem. You have to enumerate a subset of the tensor representations of this particular group. And once you do that, then you're basically 5 Cauchy-Schwarz inequalities away from a sort of practical statement about how useful this protocol is. So we can do some pretty cool things. And usually I give the slides to experimentalists, and then they're very interested in like the precise details on how this is affected by particular types of noise. But I'm not going to talk about this now. But what I want to focus on here is that the interesting thing here is that we're using some really abstract mathematics to solve an extremely concrete question. And this is what I find enjoyable. So I enjoy doing these kind of things a lot. And almost always in the future, you'll find me basically talking about representation theory on any given day. But really what I'll be solving is trying to solve problems like this. So this is sort of a short example of a particular thing that I have done in the past. Now, what do I want to do in the future? Well, I've talked about characterization procedures, but I haven't really talked about these error mitigation techniques yet, right? So in the second slide, I gave you this second feedback loop between error mitigation techniques and characterization tools. And this one is much less explored than the first feedback loop, which is essentially the one that I talked about now. It's really something for engineers. And now, like in the future, the near-term future, I really want to focus on this second loop and say, okay, how can we create characterization tools that really help build these error mitigation techniques? And also, how can we build better error mitigation techniques based on the characterization tools that we already have? Because the mantra here is basically that the first step to mitigating some type of noise is knowing what that kind of noise is, or at least knowing something about it. And I want to dive into a really concrete version of this. It depends on how much time I have. When did we start?
You have about 2 minutes left, give or take.
Oh, okay. In that case, I'm going to skip a slide, I think. So the nice thing, I'm just gonna do this then. So error mitigation is, so as I said, it is a way to sort of post hoc fix errors that happened in your algorithm. And one of the ways where this is, one of the places where this is particularly effective is in something called variational algorithms. So a variational algorithm is basically a quantum computer and a classical computer working in tandem. And these are extremely cool objects, and people at CWI might care about them because a lot of the computation is actually classical. So what you do is you set some optimization goal, maybe the minimal eigenvalue of some Hamiltonian that you care about, and you have the optimization you give your quantum computer some parameterized program to run, and it outputs some number. And then you say, okay, I'm going to feed this back to my classical computer. And this classical computer is then going to say, okay, based on that and a classical optimizer I have, I'm going to propose new parameters. And they sort of work back and forth until they find the optimal parameters and maybe solve a problem. And the nice thing about this is that you can do a lot of the computational classically, which makes you happy because quantum computers don't work very well and classical computers work quite well. But the quantum computers don't work well enough even to do this. So in general, people start building these very elaborate systems where you first try to calibrate the noise in your quantum device, and then use that noise to feed back into your update cycle. And there's a bunch of like really cool procedures that people have done, people have created, and they sort of look like this randomized benchmarking. In particular, what people are trying to do is they're saying, okay, let's learn the effective noise on some test circuits. We're going to run some test circuits here, and then we're going to learn the effective noise, and then we're going to use that to sort of dynamically update our optimization model in the classical computer. And this already sounds like, hey, we're just testing a bunch of random circuits. So we should be able to use these sort of advanced characterization procedures to actually help us do these mitigation procedures more efficiently. And this is the thing that I really want to talk about, what I'm really going to care about in the next year and a half or so. And it's something called shadow tomography, which is really a misnomer, because what you should really be calling it is randomized measurement. And in some sense, it's like randomized benchmarking, but on steroids. So instead of doing random sequences with the nice inverse, you just do random sequences and you try to learn something from this soup of random data that you get. And it turns out quite magically that this works. You can get like really explicit reconstruction guarantees on various interesting observables. And for the people that are into this, this shadow tomography is essentially a quantum version of sort of randomized low-rank matrix reconstruction techniques that have also been really popular recently. So if anyone knows a lot about them, I would very much like to hear about that, because we're very much still in the beginning of these kind of techniques, and there's lots of stuff that we can still learn. But the goal for now is to use these sort of low-rank reconstruction, like randomized low-rank reconstruction techniques, to improve mitigation strategies, in particular these sort of mitigation by learning strategies. So that's goal number one. And then the second goal, which is something that I really care about, is I really think that randomized benchmarking, even though we are only extracting one number now, we should be able to use it as a randomized measurement scheme as well. So in particular, I think it's a self-randomizing shadow process tomography scheme, which is a very technical way of saying that this object should also be useful for mitigation strategies. All right, so take-home messages. Characterization and mitigation are a fundamental part of near-term quantum computers, because near-term quantum computers are noisy, and there is just nothing we can do about it. We have to deal with this noise explicitly, at least until quantum error correction becomes a thing we can actually do. These characterization tools are mathematically interesting in their own right. So if you like representation theory, you can come help us build better characterization tools. And characterization and mitigation can inform each other. All right, and I think that puts me at about a minute over time.
Thanks a lot, Jonas. Time for one question, and as before, you can either type something in the chat or you can raise your hand in the Zoom. Felix, go ahead.
Yes, so I was wondering, so in some sense, it seems like the sort of error correction or something always adds some sort of overhead to your algorithms. And I'm wondering, so coming back to Harry's talk, can this somehow destroy the complexity analysis of these kind of quantum algorithms, that can it kind of block the quantum supremacy?
No, I mean, I think maybe some types of advantages, but if you have an exponential separation in complexity, then this is not going to make a change. So typically an error correction procedure gives you an exponential suppression in error with a polynomial increase in resources. Although I have to double check. There's an exponential, you typically do exponentially better.
Okay. Yeah.
I think it's even better than that, right? I think at least in theory, the overhead that you want to do if you want to protect a polynomial size computation from noise, constant level of noise, you can do that while increasing the size of your circuit by a polylogarithmic in n
it's
factors,
even better than that.
something like log n to the power 3, which from a theory perspective is very good. But from a practical perspective, there's like large constant factors there.
Yeah, the problem with quantum error correction is not so much the scaling as the fact that the constants are big.
Yeah. Okay, I see. Thanks.
And there's a lot of ongoing research sort of trading off different code types with different noise levels. And this is like a big sub area of the field of quantum information.